Okay. Let us get started with our interactive problem session. So, this problem was posted in homework 2 as part of the mathematical methods and techniques in signal processing offered at IISc in 2017. So, the reference to this material is Stark and Woods. So, here is the problem. Only one of the switches S1, S2 and S3 is active at a time. Switch S1 closes twice as fast as S2, switch S2 closes twice as fast as S3. The signals are normally distributed as follows: A is normal with mean -1 and variance 4, B is having mean 0 and variance 1, and C has mean 1 and variance 4. So, basically you have these switches which will operate and then you get some received signal X. What we want are the following. First, what is the probability that X is less than or equal to 1? So, I receive some X, what is the probability that X is less than or equal to 1? The second question is, given that X is greater than -1, which signal is most likely transmitted? Okay. So, using your basics in probability, how you would go about solving this problem. So, this problem will be solved by Shaunak Roy.
So, this problem is let me go through the problem once and then we will try to solve it. So, we have a receiver which is connected to 3 switches A, B and C via the switches S1, S2 and S3 which is sent to, and X is the receiving side. Now, a very important condition that I have underlined over here is only one of the switches S1, S2, S3 is active at one time. S1 closes twice as fast as S2 and S2 closes twice as fast as S3, and the random variables A, B and C are normally distributed with the following mean and variance as given here. We have to first calculate what is probability that X is less than or equal to 1, and next one is, given X is greater than -1, which signal is most likely transmitted. So, we will start working with the first problem. Probability that X is less than 1 is equal to now this is exactly the reverse marginalization what we are doing over here. Now, this particular quantity that we have over here, this is nothing but probability that X less than or equal to 1 given Si is active means probability that A is less than or equal to 1 for I equal to 1, probability that B is less than or equal to 1 for I equal to 2, and probability that C is less than or equal to 1 for I equal to 3. Now, let me just write the normal distribution function. So, if we have considered a random variable m with the normal distribution having mu mean and sigma variance, we have Now, this is the standard normal distribution equation. We will do a small modification over here to make our life a little easier. Let us consider y equal to m minus mu by sigma. We will do a substitution. This implies that dy is equal to dm by sigma, and the limits of integration changes to minus infinity remains same, and some b dash which is nothing but b minus mu by sigma. That means, now if after doing this substitution we have probability m less than equal to b is equal to minus infinity to b dash, which is this value over here, 1 by root 2 pi into e to the power minus y square by 2 dy. This is basically, if you now look at the RHS, you will have y less than equal to b dash equal to b minus mu by sigma, where y is equal to m minus mu by sigma. So, this obviously looks a little less messy. As you can see, this is a 0 mean and variance one probability distribution. Now, we actually try to solve the problem. So, what we have to actually solve is these values over here that we have to solve. Just let me open a new page. So, probability that A is less than 1. Now, we will just substitute in the normal distribution function that we have done before, is nothing but probability that y is less than. So, we have over here m minus mu by sigma. We are exactly going to do that substitution, and let us just check the normal distribution mean and variance of A, which is given by minus 1 comma 4 over here. So, that means this boils down to minus of minus 1, which is the mean, and I put the variance 2. This is equal to probability that y is less than 1. This comes out to be 0.8413. Similarly, probability that b is less than 1 is probability that y less than equal to 1 minus 0 by 1 is equal to probability that y is less than 1 is the same value 0.8413, and next we have probability that c less than equal to 1 is equal to probability that y is less than equal to 1 minus 1 by 2. This is equal to probability that y is less than 0 equal to 0.5. All these values are calculated from the normal distribution table. Now, this is what we require for the first problem. I will also write what we require for the next second part of the problem, and then we are going to assemble the problems together. So, for 2, So, this is for 1, that is what we need. Sorry, let me just write this. We have to calculate probability that A is less than minus 1 is equal to probability that Y is less than minus 1 minus of minus 1 by 2, which is probability that Y is less than 0 equal to 0.5, probability that B is less than minus 1 is probability that Y but this is not the only thing that we need here. We basically have to calculate a probability of x greater than minus 1, right. So, this implies that basically we are looking at the reverse order. That means, what we are going to use over here is, let me just write it over here. We are basically want to calculate this thing. So, probability that A is greater than minus 1 is nothing but 1 minus probability that A is less than equal to minus 1. So, that is what we are going to substitute over here for all A, B, C, and just we have this thing, probability of A greater than minus 1 is 0.5. This implies probability that B greater than minus 1 is 0.8413, implies probability that C greater than minus 1 is equal to 0.8413. These values are also calculated from here. Now, we actually solve the problem. So, if you look at the first equation that we have here. So, what we have to do? We have already calculated P A greater than 1 less than equal to 1, B less than equal to 1 and C less than equal to 1, all the probabilities over here. We are going to put that over here, but we also need this probability that S I is active, that we do not know, it is not explicitly mentioned in the question, but what is mentioned is that S 1 closes twice as fast as S 2 and S 2 closes twice as fast as S 3. So, what we are going to do? We will do a simple ratio, that is probability that S 1 is active is to probability that S 2 is active is to probability that S 3 is active is in the ratio 4:2:1, which implies probability that S 1 is active equal to 4/7, probability that S 2 is active is equal to 2/7 and probability that S 3 is active is 1/7. Now, we have all the tools that we need to solve question number 1. So, now let us solve 1. Probability that x less than 1 is, so we have this 0 y less than equal to 1, this a less than equal to 1 into 4/7 plus again 0.8413 into 2/7 plus 0.5 into 1 by 7. So, if I just write it over here, this comes out to 0.7925. We are done with the first part. Now, in order to solve for the next part, that is solving 2, in the same way we will first calculate this thing. Probability that x less than minus 1 is 4 by 7 into 0.5 plus 2 by 7 into 0.1587 plus 1 by 7 into 0.1587, which is equal to 0.3537, but we really need this, right. You need probability of x greater than minus 1, this is 1 minus probability of x less than equal to minus 1, which is given by, which is 1 minus 0.3537 equal to 0.6463. But what we really need is, once we have calculated this, okay, we have calculated probability of x greater than minus 1, but what we need is what signal has actually passed through the receiver, because we know that at a time only one signal has passed, is allowed to pass. So, we have to calculate the a posteriori probability. We have to calculate the following probabilities, that is probability that A was transmitted, that is given by this, given x greater than minus 1, the standard condition probability rule, x greater than minus 1 given x equal to A into probability that x equal to A by probability that x greater than minus 1. This is equal to 0.5 into 4 by 7 by 0.6463, that comes out to 0.4421. Similarly, we have probability that x equal to b given x greater than minus 1 is equal to probability that x greater than minus 1 given x equal to b into probability that x equal to a by x greater than minus 1. I will just write down the value over here, 0.8413 into 2 by 7 by 0.6463, that is equal to 0.3719. And finally, x equal to c given x greater than minus 1 equal to probability that x greater than minus 1 given x equal to c. There is a small mistake here, I will just, this should be b. Now, we have calculated these values, but how are we going to make the decision? We are just going to select out of these which is the largest. So, as you can clearly see that a that x equal to a given x greater than minus 1 is the highest. So, that means we can make a decision that this is the highest. So, we can make a decision that most likely A was transmitted. This particular process of making decision making is called maximum a posteriori probability decision making. So, this is very important in coding theory or wherever there involves a transmission. So, imagine that you have a channel where there is a transmitter side and there is a receiver side. So, what happens is in the transmitter side you send one signal, in receiver side you receive the particular signal, but there may be some error happening inside the channel. So, imagine that the first the transmitter side you can receive either you can transmit either a 0 or a 1, and in the receiver side you are going to receive either a 0 or a 1, but how do you know what has been transmitted with what you have received? So, for example, if what we have to calculate is if at the receiver side we get a 0, then we have to calculate what is the probability that a 1 has been actually transmitted or a probability that 0 has been transmitted. What we basically have to do is the following. So, if we have a channel like this, so suppose this is my channel, this is C. So, this is my transmitter side, that is T x, and this is my receiver side R x. So, here it can send a value 0 or 1, here obviously it will receive a value either 0 or 1, but it might have flipped because of the error, it might have flipped. Let me just write this a little bigger. So, the decision making that we have to do, suppose we have received a 0, suppose we have received a 0. So, let me write this as a random variable y and this as a random variable x, suppose. So, probability we have to calculate x equal to 0 given y equal to 0. That means, y was actually 0 was actually received at the y, we have to calculate probability that x equal to 0, and we also have to calculate probability that a 1 was probably transmitted given we have received a 0. Now, if this is bigger, that means what we have over here is this implies a 0 was transmitted. That means, there is actually we have not undergone an error process, but if this was bigger, if this was bigger, that means if this was bigger, then what we will have is a 1 was probably transmitted, that means the bit that we have received is actually an erroneous bit and we flip it back. So, this process of decision making is called or in our language you can write it as MAP. So, just let me I will go through recap the problem again. So, we have to first calculate that probability that x is less than or equal to minus 1. So, what we did, we use the reverse materialization over here, probability x less than or equal to 1 is given by this probability that x less than or equal to 1 given SI is active into probability of SI is active. We calculate the probability of SI is active later. So, the first term on the RHS is given by this, that probability that x greater than 1 given SI is active means obviously A has been transmitted if it is I equal to 1, and similarly for B and C. Now, we write the random variable function over here, we do a standard substitution given by this particular point over here, and we have a 0 mean and variance 1 expression. This will be helpful for substituting or calculating the values of A, B and C, and that is what we calculate next, probability of A less than or equal to 1, B less than or equal to 1, C less than or equal to 1, and we also calculate probability of A greater than minus 1, B greater than minus 1 and C greater than minus 1, and we also find probability of SI is active as this, because explicitly it was not mentioned, but we have was given a ratio that S1 was we have this 4:2:1 ratio, and similarly we have calculated probability S1 is active is 4/7, S2 is active is 2/7 and S3 is active is 1/7. And then we solve the first part of the problem, just substitute the values that we have calculated, we get this. In the second part we also do a similar process, that we calculate probability of x greater than minus 1 as this, which is 0.6463, and but our main question that was asked in the second part was what signal it might have transmitted. So, that we have calculated from probability x equal to A given x greater than minus 1, and we calculated these values for B and C also, and we chose the one which was highest. Apparently A is the highest over here. So, we make a decision that most likely A was transmitted. So, this type of decision making is called maximum a posteriori probability, which is very much used in communication these days. So, what we have is basically a channel which has a transmitter side and a receiver side. The transmitter side can signal a 0 or a 1 and the receiver side can receive a signal 0 or a 1. Now, let us consider the transmitter side as the random variable x and the receiver side random variable y. Suppose we have received a 0, then what was transmitted? We make a decision in this following way. We calculate probability of x equal to 0 given y equal to 0, receiving a 0 over here, and if it is greater than probability that x was 1 was transmitted given we have received a 0, we make a decision that a 0 was transmitted, that means an error has not happened. This type of decision making is called maximum a posteriori probability or MAP decision, and the probability that we calculate is based on what the channel is. So, if the channel is a AWGN channel, we will have a normal distribution. If it is something else like a standard BSC channel, we will have some different value of mean and variance or whatever be the distribution given. So, I am not explicitly mentioning the distribution over here. This is the point where how we make a decision, how we make a decision in the MAP process. So, in this particular problem we have a slight difference, we have 3 signals and we are receiving the following signal, the same ABC signal on the receiver side. So, here it is basically a ternary alphabet. In standard communication we have, since we have bits, it is basically a binary alphabet. So, with this we end solving this problem.